All right, students. So since we weren't able to meet this afternoon, I've decided to make a video here showing a couple of problems here in sections 3.5, 3.6. What I really want to say there and emphasize too is that, this assignment's not due until after spring break, but I would definitely highly recommend that you guys are looking at it over spring break. And the assignment here on these two sections here is actually 37 problems. Get started on it, and so that you're not waiting to the last minute. Try to get that all done when we come back. So 3.5 is titled the algebra functions and composite functions. It's going to show us some ways to combine functions together, and we'll talk more about how we can do this. So the first couple ways we can combine a function are pretty straightforward. Adding, subtracting, multiplying, and dividing to make new functions. So it's going to give you the definitions and do an example. So if f and g are functions such that x is in the domain of each of the functions, then we can actually combine the functions together and make the following four. The sum function f plus g of x, which is f of x plus g of x. The difference function f minus g of x, which is f of x minus g of x. The product function f times g of x, which is f of x times g of x. And the quotient function f over g of x, which is f of x over g of x. However, in that last one, that quotient function, we've talked before about how division by 0 is undefined. This function only makes sense whenever the denominator g of x is not equal to 0. Okay, so now it's going to do that and combine these functions together in this next example. They gave me the graphs of the function f here in blue and the graph of the function g here in red. And we're going to combine them, find the sum, difference, product, and quotient function, and actually evaluate them at some particular values. And we'll be using the graph to do that. So let's find f plus g evaluated at -2. So by the way we defined the sum function in the previous slide, it's f of -2 plus g of -2. Just use the graph to find these values. Whenever x is -2, the corresponding function value f is 4. Whenever x is -2, the corresponding g value is -1. So it's going to be 4 plus -1, 3. Let's go find the difference function f minus g evaluated at -1. That's going to be f of -1 minus g evaluated at -1. Getting those values from the graph, f of -1 is +1, and g of -1 is -2. So this is 1 minus -2, really 1 plus 2, which is 3. F times g evaluated at 0 is going to be f of 0 times g of 0. F of 0 is 0, and g of 0 is -3. So let's go multiply those values. I get 0. It's a product. And then now the final one, the quotient function, f over g evaluated at -1. Way that's defined, it's f of -1 divided by g of evaluated at -1. And just use the graph. F of -1 is 1, and g of -1 is -2. So this is going to be 1 over -2, and going to divide those, it's going to be -1/2. All right, so that was actually pretty simple. Just using the graph to find these function values, adding, subtracting, multiplying, and dividing, they're pretty straightforward. Okay, the issue really is going to come in on these four right here. Maybe the question about domain. So we want to show you the way to find the domain of these new functions. But before we can show you that, we need to talk about how to do the intersection of sets. So we've talked before about the symbol U, which was union, and united two sets together. This symbol here, the upside down U, is actually called intersection. Let's go ahead and read the problem and see how we're going to get this guy evaluated here and find the intersection. So graph the intersection of the given intervals on a number line and write the set interval notation. All right, so intersection is probably pretty straightforward. It probably means what you think it's going to mean. Intersection just means where do they intersect or overlap each other. So the best way to really see this is to do it graphically, like they're saying. Go graph the first set and then graph the second set and see the values for which they both share and overlap. So I'll draw a number line here for us. -9, -5, -3, and +2. The first set was all values between -9 and -3, so these values are right here in the number line. The endpoints here have parentheses around them, so they should actually not be included. So open circles graphically, indicating that they're excluded out. And now I'll go graph the second set, which is -5 to 2, the values here between -5 and 2. This time the endpoints have square brackets around them, indicating that we should be including them. So I put closed circles in this case now around those endpoints. So where's the intersection? Where do they overlap? You can see that they overlap each other right here in between the values of -5 and -3. That's the intersection. Values that they both share. Okay, but now let's go and talk about the endpoints here. Are the endpoints -5 or -3 included or not included in the intersection? Well, -5 is going to be included because he's contained in both sets. So close circle here. However, -3 is actually not going to be included in the intersection because he's not included in that first set. So since he's not included in that first set, he's not included in the intersection. Here it is in interval notation. The values between -5 and -3. Again, brackets because the -5 is included, and parentheses around the -3 because he's not included. The word I would say for this one, the keyword is overlap. All right, and now that's going to play a role here when we're finding the domain of these new functions we just created. So find f minus g, f times g, and f over g, and then determine the domain for each function. When we have the two functions, f of x is the square root of x, and g of x is x plus 18. So first, let's go find f minus g of x. F minus g of x is f of x minus g of x. So we subtract the functions, square root of x minus x plus 18. You really should be careful and put the parentheses around this because the entire function g of x ends up getting subtracted. So putting the parentheses there to remind you to distribute the negative and then really subtract every single term. Subtract the x and also minus the 18. That's as simplified as we can get because there's no like terms to combine. All right, so that is the difference function. Let's talk about the domain though. So when they defined these new functions for us, they said these are only defined for x values that are in the domain of both of the functions. So what I need to do is find out the domain of f, find the domain of g, because this new function only makes sense where they both make sense. So let's see, domain of f. Look at the function f, what's his domain? We've talked about this one before, the square root of x. You can only take square roots of things that are non-negative. It's only going to be from 0 to infinity. And while the domain of g is this function x plus 18, and he's clean in that he has no division, no square roots. His domain is all real numbers from negative infinity to infinity, and he's going to make sense everywhere. Okay, so now the domain of this new function we just defined, by combining those together, f minus g, well, this only makes sense for x values that are in the domain of both of those functions. So it's really the intersection of those two sets, and 0 to infinity intersected with negative infinity to infinity, the overlap is 0 to infinity. And that's where this new function makes sense. All right, the fifth way to do this and combine functions together is by composition. And that's denoted by this open circle notation. So say we're given functions f and g, the composite function f composed with g of x is defined as f of g of x. So you're going to take one function and put it in to the other function. So let's go ahead and show you two examples of doing that. And then we'll come back and talk about the domain. All right, it's right here. So it says, given the function f of x, which is x squared minus 7, and the function g of x, which is 1 over x plus 6, let's go find f composed with g of x, and then also we're going to find g composed with f. So let's see if we can do this as simply as possible. F composed with g of x, which is f of g of x, meaning g of x is inside the function f. So we'll take g of x and we'll put it inside the function f. So it's going to go in for the x in that function. So 1 over x plus 6 squared minus 7 will be the composition. My math lab might have you simplify that out a little bit further, but for the purposes of this video, I'm going to leave it just at that and just show you how composition works, that you put one into the other one. All right, well, the next part says find g composed with f, and it's going to be important that you understand that order matters. Because now I'm doing g composed with f, which is g of f of x. So now f is the one going in the function g. So I'm going to erase this, because now what's going to happen is the function f is going to go into the function g. So the composition would be 1 over x squared minus 7 plus 6. And that's the composition. That would actually simplify it here pretty quickly. Let's just go and do that quickly by combining like terms. Negative 7 plus 6 is negative 1. So those are two compositions created by putting one function into the other one. Let's go back to the previous definition and talk about domain for the composition, because composition is really a chain of functions that the x value is going to go through the function g first, but then that output is going to go into the function f. So to be in the domain of the composition, it's got to be able to pass through that entire chain. It's got to go through g, and then whatever comes out, g of x, has got to be able to go through f. So here's how the book talks about having to find the domain of a composition function. First off, find the domain of g, because it's got to be able to pass through g first. And then whatever comes out of that, g of x, it's got to be able to go through f. So then we'd have to exclude any values for which g of x is not in the domain of f. Okay, so I'm actually going to show you the examples here, the ones we just did, and talk about their domains. First, let's do f composed with g of x. So then this was g of x going through first, and then that was coming out and going through f of x. Look at g of x. 1 over x plus 6. The guy himself can't take a negative 6, right? So domain of g of x, it can't be negative 6. Negative 6 doesn't even pass through g, let alone the entire composition, making the entire chain. It can even pass for the first part. All right, so that's one value we know is excluded out for our domain of the composition. But then whatever comes out of g of x is going to be able to go through f. And what's the domain of f? Well, f is x squared minus 7, and his domain is all real numbers. He can take anything. So with that in mind here, the domain of the composition is actually going to be all values except negative 6. So the domain of the composition f composed with g is also all values except negative 6. As an interval, maybe negative infinity to negative 6, negative 6 to infinity. But negative 6 is the only one that's bad. Oh, let's go and look for the other example here. G composed with f of x, which was g of f of x. So now the chain's kind of reversed, and then it's got to go through f first, and then that's got to be able to go through g. Look at the function f of x, x squared minus 7. He can take anything. All x values are going to be able to pass through that first part. But whatever comes out, it's got to go through g. And g can't take a negative 6. So the output f of x cannot equal negative 6. And let's just go find out what that value would be, the one that we're going to have to throw out here for this domain of a composition. So I'm solving this, moving the 7 over, taking the square root of both sides. Looks like plus and negative 1 would be bad. The domain of this composition does not include 1 or negative 1, because while these values are going to be able to go through f, those outputs are going to be negative 6, and g can't take a negative 6, so they're out. So maybe write in the domain and the interval notation, the domain of g composed with f is negative infinity to negative 1, negative 1 to 1, and then 1 to infinity. He is 1 to 1. I'm just going to put here yes. For b, the next one, this function x squared, a very common function, is he 1 to 1? Let's go ahead and see. Let's go and drop a horizontal line. Let's go and do the one they have here at y equals 4. And you would see that the graph actually intersects that horizontal line more than once, here at negative 2 and at 2. So it's actually not 1 to 1 in that particular y value, 4, corresponds to two different x values. It's not going to have an inverse. So that's kind of important to kind of note, a very common function x squared, he is not 1 to 1 and actually doesn't have an inverse on that domain. Here is this function, the cubed root of x plus 2 plus 3. It's going to drop horizontal lines on this one. There's 1, only hits once. Yeah, he passes. Each time we draw the horizontal line, it only intersects one time, so it is 1 to 1. And then how about this polynomial function right over here? Drop a horizontal line. Let's do the one that they've drawn right here. Bam, bam, bam. It hit and intersected that graph 3 times. It is not 1 to 1 because that particular y value there is corresponding to exactly 3 different x values. And you can't do that. All right. So I've shown you how to find the inverse function, that it is just reversing the correspondence, but usually our functions are given in the function notation f of x. So how do you find the inverse function in that case? It's actually an algebraic exercise. It's a 4-step process, and this is the only way to do this. This is the only way to find the inverse of a function that was given that notation. Let's go ahead and talk about the process, and then we'll go and show you the example and actually doing it. So first off, what you do is you change f of x to y. So then now we have an equation in the form y equals some expression. And then because the inverse function is going to reverse the correspondence here, it turns out that the coordinates of the relationship actually get flip-flopped too. So we just interchange x and y here, and then now solve for y, and that actually will be the inverse function. And so then the last step says, change the y back to the inverse notation f inverse of x, as we actually found it now. And there's probably some simpler examples there first, just kind of work with this 4-step process. But I picked this one here because I want to make sure you guys can see an example of it worked out. They tell me this function f of x equals 3x minus 8 over 5 minus x is 1-to-1. So go ahead and take that, and that it's going to have an inverse function. And let's go find its inverse function. So it's a 4-step process like they were just talking about. And what you do is you replace y, f of x with a y. So that first step's not too bad. Just replacing f of x with a y. And the second step's not bad either. It's just rewriting as well, because they had said interchange x and y. So wherever you had a y, at y, it now becomes an x. And wherever you had x, it now becomes a y. Oops, it's a 3y minus 8. 3y minus 8 over 5 minus y. So the first two steps are pretty simple, just rewriting. It's really the third step, which is the algebraic portion, where now we have this relationship. We need to solve for y. So I'm going to go get a different color here, because if I'm solving for y here, I'm going to remove the denominator, multiplying both sides by y minus 5. As long as we do it to both sides, we're still good. And then that would cancel there. Okay, so then we just have 3y minus 8 there on that right side. And here on that left side, if you distribute the x, it's 5x minus xy. All right, good. No more fractions. We're trying to solve for y, so let's go and get all the y terms to one side and everybody else then to the other side. If I'm trying to avoid these negatives, I think what I'm going to do is I'm going to move this xy over to this side and move this negative 8 to this side. So we'll add 8 over here and also add xy over here. And the reason why I'm doing that again is because I want all the y terms to be on one side of the equation. So 3y plus xy on this side. I move the 8 over here, and now it's 5x plus 8. All the y's are there on that right side. Okay, now this next step is the one that I think some students might have not had known exactly what to do in this next step, because they know they want to get the y alone, but they're a little stumped because we do have two variables, x and y. So the thing is, on the right side, everything on that right side does have a y. So go ahead and factor out that common factor. Factor the y out of the terms on that right side, and that would leave a 3 and an x. And then to now get the y completely alone, it's being multiplied by 3 plus x. Let's go ahead and divide by 3 plus x. And then now our y would be alone. All right, we got it. Y equals 5x plus 8 over 3 plus x. And then that last step says, go and give it its proper name. He's the inverse function. 5x plus 8 over 3 plus x. There's actually a couple ways you can check this answer to make sure that he is the inverse function. The one that I kind of like the most is picking an x value, putting it into the original function, and seeing what it ends up going to. And then going to my inverse function and just reversing that, putting in the function value and making sure that it goes back to the original x value. So that's one method that I prefer to try to check to make sure it is. Let me go and demonstrate that, because, it's a kind of a nice thing to be able to check your answers here to make sure this is doing the right job. So this is what I was trying to say. You can pick an x value. I'm going to pick 4. I'm picking 4 because it'll actually work out pretty nice in terms of the calculations here. Because when you put it into the original function, f of 4, that would go to 3 times 4 minus 8 divided by 5 minus 4, which is 12 minus 8 over 1. and 12 minus 8 is 4. 4 over 1 is 4. All right, so sorry for the confusion. That ended up being that this is the same value, but it's what ended up happening. I picked x, put it into the function f, ended up giving back a 4. Well, let's make sure this function here reverses that correspondence, and that if I was to put 4 in, that it gave me back the original x value that I put in. So now let's go put it in to the inverse function, this value. 5 times 4 plus 8 divided by 3 plus 4. Is that equal to the original value I had picked, x, which is 4? Let's just go and test. 5 times 4 is 20. 3 plus 4 is 7. 28 divided by 7 is 4. Okay, yeah, great. This inverse function is doing his job in that he's reversing the correspondence. I think my math lab talks about another way of maybe doing the composition and making sure that they cancel each other out and give you back just x. That's another way to check to see if it is the inverse function. We need to talk about the domain and range, though, now as well. So let me go on to the next slide, and I'll show you, we'll work out this whole domain and range problem here. So the inverse function was 5x plus 8 over 3 plus x. I'm going to write that over here. I forgot what it was. 5x plus 8 over 3 plus x. All right. State domain and range of f, state domain and range of the inverse function, inverse of f inverse. Well, before I get to that, we got to talk about what ends up happening in the property with domain and range of f and f inverse. Let's go back to our original values, our original example we did with the inverse, this one right here, how we had f and we had f inverse. So the domain of f were these values right here, and in the range of f were these values right here, their corresponding y values. Now let's go look at our domain range of our inverse function. The domain of f inverse was these values, and in the range of f inverse were these values, their corresponding function values. What can we kind of notice there about the functions domain and range and then the inverse functions domain and range? They actually just interchange. Again, all the x and y coordinates are swapped out here on the function f and its inverse. The domain of f is actually the range of f inverse, and the range of f is actually the domain of f inverse. Okay, so that's how we're going to get this done when we know that relationship there with domain and range. So state the domain and range of f. I'm going to write all this out. Domain of f, range of f, and then later on we're going to find domain and range of f inverse. Just going to get some place to write that too. Here's how you do it. What's the domain of f? We can see that by looking at the function. What value would be bad for that function and not giving a number back? Look at the denominator, 5 minus x. 5. 5 would be bad. This guy can't take a 5. X can't equal 5. Again, in the interval notation, everybody to the left of 5 and everything to the right of 5. That's the domain of f. That's pretty quick. You know, we've been talking about finding domain for the previous unit as well. We should be able to do this. Let's go to the inverse function now and find his domain, because we were already used to doing domain already. This inverse function ended up being 5x plus 8 over 3 plus x. What's the value is bad there? What makes the denominator 0? 3 plus x? Negative 3 would be bad. 3 plus negative 3 is 0 and undefined. Doesn't give me an answer back. So the domain of f inverse is everywhere but negative 3. And there he is in interval notation. And then now, since we know the relationship of how the domain of f is actually the range of f inverse, and how the domain of f inverse is actually the same as the range of the domain of f, so then those just interchange. You know, the domain of f is now the range of f inverse. It's just copying, because I know they're going to be the same. And the domain of f inverse is actually the same as the range of the original function f. So I just copy that there too. There we go. Okay, and this is actually the last problem here in this whole inverse discussion. Use the graph of f to sketch the graph of f inverse. So they've actually given me the graph of the function f and some points along that graph. And now let's go find its inverse function f inverse. Well, the simple way to think about this is because, again, the relationship gets reversed between the function and its inverse function. look at this first point. It was -4, 2. So whenever x was -4, it went to the function value 2. So the inverse function is going to reverse that and send 2 back over to -4. So 2, -4 is going to be on the graph of its inverse function. And that happens for all the points and all the coordinates of that on the graph of that original function. All of them get interchanged. -3, 3. Well, on the inverse function, it's going to be 3, -3. 0, 4. Now it's 4, 0. 5, 5. Swap out those coordinates. Well, it's actually also 5, 5 because they're the same. But then that would be some points on the graph of the inverse function. Let me go and show you because I've already made the graph here for us. Here's the graph of its inverse function. So here is y equals f of x. Then here's the graph of its inverse function, y equals f inverse of x. Because of the coordinates just interchanging. And another way to say this is the following thing. This is that these graphs, the function and its inverse function, are symmetric about the line y equals x. So it's, again, that's another quick way to kind of make sure you found the right inverse function. If you just want to graph them and made sure that they were symmetrical about the line y equals x, that's a quick way to do it too. All right, we're actually on the last problem here for today's video, and it's actually not in those two sections, 3.5, 3.6, but it's a question that I want to make sure you guys are able to see because it's on the homework assignment, 3.5, 3.6. Even though we actually already talked about difference quotients in the previous section, this one right here actually didn't have the viewing example available to you, so I wanted to make sure I made the video to discuss it. So again, difference quotients, we actually really don't need to know exactly what they all mean. It's something later on for students that are going into calculus. That's something that they'll be dealing with there. But algebraically, we should be able to show you how to simplify it down because this is a prerequisite for that particular course. So the function f of x in this case is a square root function, 15 times the square root of x. When I go find a difference quotient, I don't jump all right in and try to get it all simplified all at once. I take small bites and find out each piece separately, and then we'll put it all together at the end. So I see here in the difference quotient, they have the expression f of x plus h. I need to find that first. F of x plus h, the thing in the parentheses is x plus h, so then that will go into the function for x. So it's going to be 15 times the square root of x plus h. Okay, let's go and look at the numerator. Again, kind of doing small bites here, piece by piece. The numerator has f of x plus h minus f of x. So then that's 15 square root of x plus h, f of x plus h, we just found it, minus f of x, so minus this thing right here, minus 15 root x. And then maybe that simplifies just a little bit in that, they both have this 15. It's a common factor. 15 times square root of x plus h minus the square root of x. And then now the difference quotient, so I'll put here dq, is f of x plus h minus f of x all over h. So it's this over h. But we need to simplify it. And the directions actually tell you how they want you to simplify it and saying simplify it by rationalizing the numerator. So let me show you how this is going to get done here. I'm going to get a different color because what we need to do is we need to change the expression a little bit. In the expression we have here in the numerator, we have this expression square root of x plus h minus the square root of x. When they ask you to rationalize the numerator, what you want you to do is multiply by its conjugate. The conjugate is just going to change the sign. That was subtraction. Its conjugate is the addition, square root of x plus h plus the square root of x. And we're going to multiply by that conjugate and see what happens. See it's going to actually simplify things out here just a little bit. But if you do it to the top, you need to do it to the bottom as well. So I also multiply that same value there on the denominator. Okay. Let's go and see what we have here. So yeah, we still have that 15 there on top, and we still have this h and that thing there on the denominator. But what happens here whenever you multiply these conjugates out? Square root of x plus h times the square root of x plus h is x plus h. Square root of x plus h times the square root of x will be the square root of x plus h times the square root of x. And then now the inside terms minus the square root of x plus h times the square root of x. And then the last term, square root of x times negative square root of x times square root of x. Well, negative times a positive is negative. Square root of x times square root of x is x. That's what's happening after you FOIL. But if you combine like terms, the square root of x plus h times the square root of x minus square root of x plus h times the square root of x, those actually cancel. And that's why they wanted you to do this, because anytime you multiply by a conjugate, the outside inside terms will always cancel because of those signs being different there. And I think there's actually more simplification there too, right? In this case, minus x and plus x also cancel. So it's really simplifying out our expression by doing that multiplication by the conjugate. That's just now 15h there on top, and in the denominator, h times the square root of x plus h plus the square root of x. But even that simplifies just one step more, in that the h on top will cancel with the h on the bottom because they're a common factor. And now we get the expression in the way that they want it written, with the numerator removed, having those square roots removed. 15 over the square root of x plus h plus the square root of x is the difference quotient. All right, guys, so that's the rest of this. That's the end of this video here. Have a great break, and I'll be looking forward to seeing you guys soon.